Hello, everyone, and welcome to A Propensity to Talk Density, a podcast from the experts at Bell Geospace. I'm your host today, Tyler Kern. We are thrilled to have you along for this episode of the show. And today we're talking about why density matters. We're going to dive into that topic. And we have two subject matter experts joining me today to help explain that and much, much more. First, we have Tim Wright, Director and Principal Geoscientist for Scorpion Geoscience Ltd. Tim, welcome to the show. Thanks for joining me.
Thank you very much, Tyler. It's a great pleasure. Thank you.
Absolutely. And we're also joined today by Good Poulican. She is the Business Development Manager for Bell Geospace. Good, thank you so much for joining us.
Thanks, Tyler, and thanks for hosting this event.
Absolutely. I'm thrilled to have both of you here on the show today. So before we dive into our conversation, I want to give everyone a sense of your experience and your history in the industry. And so, Tim, let's start with you. Just give us a little bit of information about your background and your experience here.
Thank you, Tyler. I'm a principal consultant geoscientist, as you mentioned, at Scorpion Geoscience Limited. We're a relatively new company based in the UK. I have a PhD in structural geology, and I've been involved in resource exploration and developing deposits for spanning 3 decades now, so over 15 years of experience. So it's been quite a while. I initially worked in oil and gas, but certainly increasingly towards minerals and mining, and of course renewables, which is a huge growth market. I've worked around the world, in Africa, South America, Europe, and latterly the Far East. And I've worked on many projects which have involved all sorts of different technologies, particularly attached to geophysics. So things like magnetics, things like gravity imaging, seismic imaging. And I'm pleased to say that I have plenty of successful outcomes for clients over the years. So that's me.
Thanks, Tim. And so I'm responsible today for Bell Geospace business development in the Eastern Hemisphere, so it's quite a large territory. However, I'm a geophysicist by training, and I like to think really that I've grown up with potential fields, so with gravity and magnetism. So I've been working with these two techniques during all my career, although in very, very different roles over the years. So I've been privileged to start my career working with gravity and magnetic as an explorer myself, both for hydrocarbons, then mineral exploration. And I went to work for a leading software company specializing in processing and interpretation of magnetic and gravity data. And now I'm back where really I think it all starts back to first base with data acquisition. And I think really that having done a full loop during my career, covering all aspects of the potential field industry exploration, has given me a unique perspective on the role of this method for exploration and how they have evolved over the last 20 years.
Well, thank you both so much for sharing a little bit more about your background. And I'm excited to draw on your expertise and your experience here in this industry as we continue our conversation today. Now, density is obviously an important topic to us here on this podcast. I mean, it's in the podcast title, after all, A Propensity to Talk Density. So, Tim, what makes density so important as we begin this topic today and as we talk about this industry?
Well, density has been certainly been very important to Gord's career. Density and magnetism, for me, are two physical properties of rocks, which really form the foundations of what we call non-invasive or remotely sensed mineral exploration. So it's really ways of seeing into the ground. And all gravity and gradiometric detection techniques are reliant on being able to detect very subtle variations in the Earth's gravity field. These can be caused by distribution of mass, so things that are a little bit more heavy, things that are a little bit less heavy, in very, very simple terms. So what we're really interested in are that some of these variations are attributable to ore deposits and valuable resources. So that's really where the most interest comes from. The story really for density actually begins with gravity. So at least in simple terms, we'll try and perhaps just describe a little bit about that for you, just to give you some background before we go into more depth. So gravity, for those of you out there watching, you'll be familiar with it. It affects all of us. It's one of the 4 fundamental forces of nature, and it's really a measure of the attraction between masses. It's absolutely universal. There's no escaping it. Every object in the universe experiences gravitational attraction to other objects. So it doesn't matter whether you're a tiny grain of sand or an enormous great star, you still feel attraction towards one another. And actually going back a long time, back to the 17th century, Isaac Newton very helpfully outlined some rules to help us explain what gravity is and how it works. And he concluded that the force of gravity is influenced by the mass of objects, but also how close they are to one another. So we can break things down into simple methods and simple techniques that we can start to understand. The objects that we see around us that have larger masses tend to experience greater accelerative forces towards one another, and conversely, objects which are of lower mass, smaller typically, maybe less dense, they experience a much more reduced accelerative force. So there's a force involved here, and that's really what the attraction is between the objects. So the reason I'm mentioning that is we have to have something that we can actually measure, and that's really where Gord and Bell come in, because they're able to measure these forces that we see around us. So I have to say, this is one little point of amusement, that I think I'm attracting the Earth a little bit more than I was before lockdown began. I put on a few extra kilos, and therefore the Earth is noticing I'm here, and I'm certainly feeling the Earth. So yeah, that's definitely something to be borne in mind. And actually, that's why I'm probably going to go for a run after this podcast to try and reduce my gravity and make life a little bit easier for myself. So that's one thing that I'm sure we're all thinking about. But I think it's important to say that weight, which is the way that we describe our sort of mass, if you like, on the Earth, is really a simple everyday measure of gravity. And weight is an important differentiation to mass. Mass doesn't really change, but weight does change, and weight depends on the mass of the two objects. So whether it's myself and the Earth or something else, the greater the sum of the mass, the more weight you'll experience. And I know Gord mentioned earlier, a really good example is that stood on the Earth, I have a certain weight. If I go and stand on the Moon, fortunately, my weight's a little bit less, so I have to do less running. So that's one thing to bear in mind. So I think based on that, going back again a few centuries to our friend Galileo. Galileo was a very smart guy, very much like Isaac Newton, and other than when he was inspiring Queen's Bohemian Rhapsody, he was also busy coming up with all sorts of other thoughts on objects and the way they fall. So Galileo went to great pains to point out that a very big sponge ball, which I will show as Exhibit A, actually should, in theory, fall at the same speed in the Earth's gravitational field as a more dense ball like this golf ball. Not taking into account things like drag and complexities, which we can't possibly cover in this conversation. But the key thing is that as long as the mass is the same, in theory, the gravity should be the same. And that's the thing that we have to take into account whenever we're doing potential field measurements. The thing that tells us whether this ball or this ball is less or more weighty is actually not whether it's red or whether it's white or anything like that. It's actually a combination of the volume and the mass. And we conveniently can simplify that to being density. So that's why density is so important to us in the nature of this conversation. We know that density and gravity are therefore intimately related. We can show that density affects gravity, and gravity is a measure of density effectively. So we can learn more about objects without really being able to see them. So even if I couldn't see the color of my red ball or my golf ball, I can still say something about them. And I can actually say that the golf ball, certainly in terms of me holding it, feels more weighty than the larger red ball. So we can actually say something about it. Also, gravity fields are not blocked by objects the way that soil or vegetation get in the way of some measurement techniques. So gravity is sort of all pervasive. You can sense gravity of an object through a wall. You can sense the gravitational effect of something on the Earth, whether you're a little bit close or a little bit further away. It doesn't matter too much. So gravity is a fantastic phenomenon that we can use to our advantage as resource explorers. So one final thing to note, really, and zooming rapidly from the 16th and 17th centuries forward to the 20th century, our friend Einstein, in a moment of equal genius, really, realized that the presence of an object, like a big heavy cannonball or indeed a planet or a sun, actually alters or warps the local gravity field. So it has a deformation effect on the local gravity field and the way that people experience gravity around it. So that's very important to us, and that's very, very important to Gord and the techniques that she uses for imaging and measuring gravity fields. So gravity is actually surprisingly weak. So as forces go, it's actually the weakest force, really. So certainly compared to the nuclear forces and electromagnetics, it's very weak. After all, we're all sitting on the Earth. I'm stood on the Earth, and if I try really hard, I can actually jump in the air, just about. and so I can overcome the entire gravitational attraction of the Earth just by jumping. So either I'm really athletic, or the Earth doesn't have a very strong gravitational field. So everything we do here is based on very, very subtle differences. And it's extremely difficult to image small objects with gravity. So the larger they are, the easier it gets for us. So that's really where Gord comes in, and her fantastic techniques and fantastic pieces of equipment. Fortunately, for those of us who are into resource exploration, most ore bodies and most features of interest to us geologists are actually very, very large. They might be millions or even billions of tons. And therefore, although they're relatively small compared to the Earth, they do deform and distort Earth's gravitational field enough for us to be able to detect it. So the key thing for us is to try and identify rocks and minerals that generate contrasts between the standard field of the Earth, the gravitational field, and things that change the local gravitational field that hopefully relate either directly to mineral deposits or perhaps are a proxy for mineral deposits. So we're always keeping our eyes peeled for anything that can help guide us. So really, by analysing gravitational fields, we can spot those features which look a bit different, and particularly if we understand the geology of the area, we can start to build in background knowledge, maybe gained from boreholes and from outcrop studies, and we can start to build a model of what's going on under the ground beneath our feet where we can't see it. So by detecting the amount of gravity and the rate at which it warps, we can actually determine what's going on, and we can get some idea of the nature of the features beneath our feet. And that is really the essence of full tensor gradiometry. And I'm sure Gord can probably expand dramatically on what I've said. So I will pass over.
I think you said almost everything, Tim. But yeah, in a nutshell, just coming back to 2 points and maybe trying to make the audience understand how we get to that subsurface. The density and the gravity. So as we said, any variation of the mass distribution is in the subsurface will incur changes in the Earth gravitational changes. And these changes that we can measure either with a gravimeter or what we use at Bell Gravity Gradiometer are tiny. This can be really minute variation compared to the planet all field gravitational strength. So it's we need really, really accurate instrument to do that. And to give you an idea of what the instrument we have on board do, the accuracy, I think, if I remember, it might be, it's not totally up to date, but it was the second most accurate instrument behind the atomic clock. So it's tiny, tiny variation. I was actually, so it's always good, interesting to go have a look at Wikipedia. And I was having a look earlier, and so we measure two things. We're going to talk today about gravity, which is an acceleration, and that's it's a force, measuring the unit is milligal. And we're going to talk about gravity gradiometry, which is nodvos. And we measure these two things. So to give you an idea, reading on Wiki, a person walking past a distance of 2 meters, and that's very relevant for social distancing, would provide a gravity gradient signal of about 1 nodvos. Okay, and that's a really small thing. So when we fly our aircraft, looking for deposits, the precision, if you want, of those measurements is about 2 to 3 nodvos. So, and we're flying at 100 meters. So that gives you an idea of what we can see, which type of movement, tiny thing we can record with the instrument. So one last thing, let's go back, Tim, to your cannonball example, and how we can go to this deposit and find understand the geology that's hosting mineralization. So let's imagine that you've shot 2 cannonballs, which are metallic, and they've landed just below ground, so slightly buried under the soil, the surface. So they're both denser than the surrounding soil. They're metallic. But let's assume that one, for the sake of this explanation, one is even denser than the other. So they've got same size, same shape, same geometry, whatever. So we fly over those 2 cannonballs with a gravimeter or gravity gradiometer. So what they're doing, because they're dense, they're pulling down the gravity field, okay? They're creating an acceleration. So when we fly with our aircraft and our instrument, we're going to see that pull is going to create a positive and acceleration that we'll be able to record, and I'll explain that later. One has a larger density than the other, so one is going to pull even higher, and in comparison to the soil, the hosts surrounding them, they are denser. So we fly over and we record this acceleration, we process the data, and what we end up with is with map of lows and highs. Okay, high when we've got a denser body, a higher gravity, stronger acceleration, and low when it's reverse. And we're going to map those transition zones, those contrasts between low and high. And that's really how we understand, or we start understanding how the geology in the subsurface is distributed.
It's really, really fascinating, and I thank you both for that explanation. And Tim, you say that rocks, while diverse and complex in their visible characteristics, are made up of minerals and matters which adheres to the basic predictable laws of physics, like you laid out a second ago. So why is that important to keep in mind when we have this conversation?
Well, it's really fundamental to the techniques and the reason that Bell have developed the FTG technique. Rocks and minerals are usually described by colours and textures. And as a geologist, normally we have samples to hold on to. Around me have some rocks which are purple, red, green, all sorts of different colours. So that's very, very easy. However, of course, the problem is that most rocks that we're looking for as resource geologists are not so easy because all the easy ones have been found. So for us, it's a little bit more like trying to play a detective role. And I sort of liken it to a Nordic noir drama where it's all quite sort of dark, it's all quite difficult, and we have to use any means we can to try and detect our targets. So fortunately, a bit like the adversaries in some of these Nordic noir dramas, rocks and minerals do, for our favour, have some predictable characteristics, and these are really important for us. We can detect them when they're buried in the ground. And as Gord has just elaborated, it's amazing how much sensitivity some of the modern techniques have and what they can tell us about what's going on in the subsurface. So for me, density and magnetism are two of the most important properties we can use to help our detective work. We know that density can affect gravity fields. So by measuring gravity very, very accurately, as Gord has described, with very high precision instruments, we can back out some quite important information on density. And that tells us quite a bit about rocks and minerals that form those rocks. So effectively, density, which we're talking about, is a very helpful diagnostic tool for many minerals and rocks. To sort of build out from that, the average density of the Earth's crust, which we all walk around on, is about 2.8 grams per cubic centimetre. So that's a fairly sort of standard measurement. It varies quite a bit, but that's about average. So anything that forms a contrast to that overall average can be measured, particularly if there's enough of it to warp the gravitational field and create a proper gravity signal. So rocks and minerals form a kind of spectrum, a density spectrum, if you like a rainbow of densities, starting very, very low and then moving up to quite high values. And I'm lucky enough that through my career, I've always had a slight fascination in collecting rocks and minerals. So I've got a few rocks and minerals to show you today to exemplify some of these the characteristics. So to give you an idea of some low density rocks, we can start off with some organic deposits. Things like coal. This is a piece of fossilized tree root, which comes from the UK, and it's really it feels quite light. It doesn't have a huge amount of mass for its volume. Its density is just over 1.5, so it would just about float in water. It might just sink. Other rocks that have quite low densities are things like graphite. So I have an example of graphite here, which came from Sri Lanka. It's quite a nice, almost crystalline example. And again, that has a density that's only just above water. So for a metallic or semi-metallic mineral, it's really quite low density. And these are the kind of features that would show up as a gravity low in Gord's precision surveys, if you have enough of them. We also have things like amber, which, although it's very, very small, is probably one of the lightest sort of rocks you can find, if you could call it a rock. This has a density which is actually lower than the density of water, and it will in fact float on water. So quite often over around the Baltic area, you will find amber washing up on the beach because it actually zooms along on the water like it's just a very, very light mineral. As we head in towards slightly higher densities, we get towards most of the rocks that we're all familiar with. So anyone who's a geologist will know things like sandstone. This is just a standard piece of sandstone. It's made of some quite interesting things called oolites, but all in all, it has quite a few gaps in it. This is the kind of thing you might find as an oil reservoir anywhere around the world. and it has a density just over 2 grams per cubic centimetre. So that's reasonably light, but it falls still into the fairly light category. As we head towards the mid-range of densities, we get into some of the more familiar rocks that those people who live on older parts of the Earth will know. We're talking about things like basalts and schists and slates, some of the metamorphic rocks, some of the big igneous rocks that you'll come across as well. So I've got an example here of some beautifully folded rock here from Scotland in the United Kingdom. And this is from the Appin group. It's Precambrian age, so around about 600 to 700 million years old. And it's got a fantastic texture, but it feels heavy in my hand. There's a fair amount of weight, and it's got a good deal of mass packed into its volume. So that's really quite a heavy piece of rock, and that will show up quite nicely against sedimentary rocks. So we can start to generate these contrasts that we're interested in. When we start to move towards metallic minerals, and some of the minerals that we're looking for resources, they can be much, much heavier. So we've got things like iron minerals. This is just a straightforward piece of kidney ore, which is hematite. This has a density of between 4 and 5 grams per cubic centimetre, which means it starts to stand out. So in places like Australia, where they have very large banded iron formations, they really do stand out on gravity surveys quite nicely. We also have things like garnet, which makes up quite a large amount of the deeper parts of the Earth's crust. This is a nice, pretty garnet from Tanzania, and it's shaped like a football or a sort of dodecahedron. And this actually makes up a lot of the crust, and it has a density of about 3 to 3.5. So it's volumetrically quite large, and we tend to find some quite interesting ore deposits associated with garnets. As we move in towards the heavier realm, we can get to something really heavy. Let me find something that's really heavy. So this is pretty dark. I don't know if you can see it. There we go, if I shine a light on it. This is a tungsten ore. It's called ferberite, so it has a bit of tungsten and a bit of iron mixed in it. This I can tell you is quite heavy. It weighs well over 1 kilo. It's maybe 2, maybe 3, maybe even 4 pounds, and it's not really very big. So compared to some of the other pieces we had, like the coal, which weighs maybe just a few hundred grams, this is getting on towards 10, even nearly 20 times as heavy. So it's really quite substantially different, and that gives us a fantastic contrast to be able to image deposits that contain tungsten if there's enough tungsten involved in the situation. But one of the most important minerals we look for are something called sulfides, and so I'll finish this section with a sulfide. Sulfides host many deposits. They sometimes hold lots of copper. They can also host things like silver. Gold is often found associated with sulfides. And this is just a nice piece of pyrite, which I wanted to show you, which comes from Peru. It's a very famous mine called Huanzala. But pyrite, I can tell you again, this is really quite heavy. This probably weighs in the region of 3 to 4 pounds, just over 1 kilo, 1.5 kilos. And pyrite can make up quite a large amount of a rock in an ore deposit, so it can actually have a material difference on the gravity gradient around it. So things like volcanic mass sulfides and porphyry copper deposits can often be detected by a gravity signature, as well as potentially a magnetic signature. So that's probably a little bit of background on why the actual mineralogy matters, because although these are individual samples, when you combine them into a deposit, the overall effect is there for Gord to detect with her very, very precise instruments.
Thanks, Tim. That was a fantastic overview and really nice to see some rocks too. That's the geophysicist talking.
Well, we've all been trapped inside for too long, so it's quite nice to be able to see a few rocks.
I don't have just one thing I want to add to you. You do great explanation here. That you said, I think, explained really well how it can mapping. We're trying to get into knowing the density. We can help, and the gravity help mineral explorer understanding the subsurface. And as you said, the most important thing is all about contrast. Okay, we do need contrast to create variation in the gravity field. We need to change the acceleration. So this contrast, as you very well described, can be either lithological change, we moving from one rock to another, a mineral to another, and the density change, and that creates a contrast that I can record with my instrument. Another thing that creates a contrast can be a change in geometry, or as we were talking earlier, shape. And what can that relate to in terms of geology? Well, that can be faults, that can be a syncline, that can be an anticline, any geological expression of deformation, of metamorphism, etc. So both of these change in property, density, and geometry are contrast for us, and that's what we record, and that's what helps us understand the geology and where mineralization lies in the subsurface.
So this might just be a question where I need a little bit of clarification because Tim, I know that this is something that you've spoken to a little bit, but what is the difference between gravity and magnetism, and how do you separate and differentiate between those two things?
Okay, well, I will give my description of this, and then perhaps Gord can expand again. This is, for me, where things get quite interesting. So magnetic imaging can detect the presence of things like our giant cannonball, which is made of metal. It would show up as an anomaly on a magnetic survey. It has a magnetic effect. Actually, somewhere in my collection of objects around me, I have a very rare piece of meteorite. So this is an iron nickel meteorite from Namibia. It's one of the Gibeon meteorites. It weighs about 1.2 kilos, so it will have a bit of a gravity field association. But more importantly, it has a very strong magnetic character. So materials like this, rocks that contain a lot of iron and other magnetic elements, can be imaged using magnetic surveying. You can get some quite nice images of features like kimberlite pipes, where diamonds are found. The ultramafic minerals, as they're known, which contain the diamonds, have large quantities of iron in them. And that actually gives them an opportunity to be able to be imaged by flying airborne magnetic surveys. Of course, magnetism won't help so much if the cannonball or if the rock is made of non-magnetic materials. And that's really where we need to understand the difference between what these techniques can offer us. So in a resource context, magnetism is somewhat limited unless you mix it together with other techniques. So whilst magnetics are extremely helpful for me as a mineral explorer, once you start to pair magnetics with things like gravity and full tensor gradiometry, you suddenly have a much more impressive toolbox with which to play. So to give you the background on conventional gravity as people have used for maybe the last 50 to 100 years, gravity tends to spot quite long wavelength trends in the Earth's surface. So it picks up large bodies of rock and contrasts, which are over many kilometers, many miles. And conventional measurements would tell us maybe that an object of a huge, great piece of igneous rock is present, but it doesn't tell us very much about the shape of that igneous rock. And it doesn't really tell us very much about how deep that rock is either. And as an explorer, knowing how deep something is does matter, because you need to know how far you're going to have to get down into the ground to find it and whether it's going to be worthwhile mining. So gravity is only really detected in one dimension. You can do it with ground-based measuring tools, gravimeters, or you can fly them in a plane, as Bell do. And so therefore, it's actually quite hard to see the shape of features. If you're looking with one eye, you can't see in stereo. You can't really see what's happening around the back or around the side of the object. So as Gord mentioned earlier, we can have something like a cannonball, which we can image as a sort of circular feature on the ground on a map. We don't really know whether that is truly a cannonball or whether it's actually a big long rod made out of the same material with the same mass. So certain cross sections aren't going to tell you very much about the object. And that's really where gravity on its own starts to struggle. So magnetics and gravity together really, really help. And they've been instrumental in finding all sorts of different deposits around the world. But the addition of full tensor gradiometry, FTG detects the pull of gravity in the third dimension, so you can start to see what's going on from the sides as well as from above. And that really is a huge, huge advantage for us. So we're measuring the rate of change of gravity. So it's not just the actual amount of gravity, it's the rate at which it changes. So I know Gord, I think, has a fantastic example of the difference between a direct measurement and a rate of change measurement. So I won't stray into that. But the key thing is we're looking up and down, and we're also looking side to side. So as a non-mathematician and as a non-expert physicist, I will leave the complexities to Gord to describe. But for me, in simple terms, using something like FTG as a tool is a little bit like having sort of hawk-like stereo vision, as opposed to just looking from a distance and just seeing one-dimensional object. So Gord, take it away.
Thanks, Tim. Yeah, well, the 3D, just to take on your last point, the 3D element is really important. Gravity gradiometry is a full 3D measurement, but we will go back to that maybe. I'll go back quickly to magnetism and gravity. And as you said very well, the main difference, they relate obviously to two very different physical property, magnetization and density. And magnetization is inherently more complex than density, and we won't go into the detail of that, but explorers use both, and they don't always see the same thing, as you very well explained, Tim. And for example, you can have rocks which are both dense and magnetized, but you can also have rocks, for example, which are dense and non-magnetized. Carbonates is one example. And you can, of course, also have rocks which can be two rocks which are both magnetized, but will have different density signature. And these differences are not a bad thing at all. On the contrary, as it often makes these two methods very complementary and helps explorer separating, distinguishing different lithology and rocks. So again, integration and complementarities are really keys in exploration, always been and will always be, I think, of method and approach. So let's go back to gravity versus gravity gradiometry. And maybe before even going there, let's go back, Tim, as you say, to the rate of what is a rate of change. And I was thinking earlier today, maybe that example is not so great. I took Tim, I'll explain later why. But to give the audience an idea, what you measure a rate of change. Okay, let's say you're driving your car, then your speedometer takes you velocity 60 miles per hour. Okay, that's your velocity at time t. No, acceleration or the rate of change of velocity will be your acceleration. It will tell you how you have changed from T0 to T1 to get from 0 to 60 miles per hour. That's the rate of change. And it can be in one direction, but it can also move all sides. Obviously, it can be 3D. And so that's the difference really between a measurement and its gradient. Now, it's a bit, I was saying I was a bit careful to use that analogy, but because gravity itself is an acceleration. So gravity gradiometry is going to measure the rate of change in the three directions of that acceleration. Okay, so in a nutshell, as Tim said, gravity field is a vector. It's a three component, Gx, Gy, and Gz. And we always measure classic conventional instrument, measure the vertical, the Gz component. And what we do with gravity gradiometry is that we measure the three vector, we measure the rate of change in the three direction. So we end up with 9 measurements, which is a hell of a lot of information, but that's good. The more information we have, the best it is. So that's the difference. And a very simple way of explaining what we do is it's not the black box. There's no magic science. There we have accelerometers on board. That's what we do. Your iPhone has accelerometer on it too. So that's exactly what we do. When you have something denser and you fly over it, it's going to make your accelerometer spin faster. And that's how you record that pull in a gravity field. When you have a single accelerometer, you get the gravity. No, if you have two mounted on the same platform and you measure the difference between the two, well, you measure a rate of change of the acceleration. And that's what we do with gravity gradiometry. And there is another great advantage of measuring difference between pairs of gravitators is obviously we do airborne survey. We want to measure something which is really tiny, and we fly in something which is moving a lot and quite fast. So the aircraft, it would be the same if you were doing it in a car. The vehicle has its own acceleration, and it creates a lot of noise. Actually, the noise, the acceleration of the aircraft is far superior to the acceleration we're trying to measure. So going back to those opposing pair of accelerometers, the great thing about it is that by taking the difference, they're not far apart. They're only 30 centimeters apart. So the noise they record in position A, position B is almost the same. So by taking the difference, we kind of remove the noise of our platform, of recording platform. So that's really the great trick here in the measurement.
So when it comes to gravity gradiometry, when you think about this, what is it capable of? How is it still developing? Where does this continue to move forward as you think about the future and as you continue to refine this approach when it comes to gravity gradiometry?
Yeah, I think there's still a lot of exciting days ahead. Well, Tim, before I moved on the previous question, we talk about how deep. You took the example of kimberlite, and we talk about density. Yes, we need to know how what's the density of the deposit to be able to know which type of rock they are. We also need to understand the geometry. Okay, we can't go and drill a hole if we don't understand how deep that kimberlite is or how deep that intrusion is. So, to understand both geometry, depth, and shape and density of the deposit, there's a lot of things that we can do to I would say, massage the data. And that's where there are a lot of things happening at the moment in the field. And I think there'll be more things happening. We've got a lot of good toolbox to help us. And with computer power ramping up, high performance computing, we can do faster, larger, and more complex model of the subsurface using our gravity gradiometry and magnetic data. As always, success of these approaches in exploration always rely, I think, on good data and integration with other data sets. We need to the one thing which is unique is the geology. So we need to contain our interpretation, constrain it with our geology to get plausible Earth model from the data. There's also, the more we go, the more interaction, multidisciplinary interaction there are, and we find always a new clever way to image the data. For example, at Bell, we use tertiary imaging, combining several data sets together, and that helps getting a more efficient, easier to read imaging. I think another things which is really changing the field, of course, and that's that can apply to the whole of exploration geophysics, is that we entering really the era of what you call multiphysics and machine learning. So we can integrate and explore multiple data sets faster and better than we've ever done. I think that's only the start. It's really starting in mining, but it will certainly ramp up in the coming years. So that makes me really confident that gravity gradiometry data will play an important role in mineral exploration, in particular as we're looking more and more for deeper targets. And I don't know, we didn't talk about the Bushveld complex team today, I think, but if we take these two, going back, we have a project currently at Bell where we're looking at one of the satellites of the Bushveld complex, which is called the Molopo farm. And there's a lot of exploration potential, but to try to make that more efficient is that we're currently applying multiphysics and machine learning to legacy gravity gradiometry data and getting exciting results. So all that is coming up, is new, and I think it's really really exciting stuff.
Tim, anything you wanted to add from your perspective?
No, I think that sounds absolutely great. I think it's a fantastic description, and I think it's helping people to understand that the techniques that are available are evolving really quickly behind the scenes. And the early days where some of these techniques were tried out and people weren't quite sure whether it was working or not, there are so many examples now where the technique can be proven to work, that you can actually take confidence and you can trust the data. And as an explorer, in charge of budgets and in charge of people working out in the field, you have to be able to trust data and you have to be able to trust models. So I think that's one of the biggest steps forward, is using all of the database that's available to us, not leaving it tucked away in a drawer, but putting it into a computer, putting it into very smart people's minds and saying, right, what are the patterns in here and what do we need to do to test them? And that gives you a workflow which is more straightforward. If the answer is you have to drill a borehole, you go and drill a borehole. If you need to go and collect an outcrop sample, you go and collect an outcrop sample. The whole process becomes more efficient. And there's one thing miners really like, and that is efficiency. So I think that's the bottom line.
Fantastic point. So, Tim and Good, as we begin to wrap up our conversation today, let's tie a bow on this. Are there any final thoughts, any final statements you want to give us before we wrap up this episode for today? Either conclusion statements, summaries, or anything that we haven't touched on up to this point. Tim, let me toss it to you first.
Yeah, well, one thing I would say is maybe just an overview of how techniques like FGG can be involved into mineral exploration in the real world. Theory is great, but what does it actually do for us? How do we actually use these techniques? So one thing that I can say for sure is that it's extremely difficult to spot gold nuggets. I've got a little gold nugget here. This is from Zimbabwe, and it's a beautiful little thing trapped in quartz, but you're never going to be able to spot it remotely, not even with the precision of instruments that Gord has. So fortunately, the one thing we can say is that if we have characteristic signatures of these deposits, we can go and find them. And certainly things like buried porphyry deposits, which is a particular type of deposit, can contain millions of tons of things like copper and gold. So therefore, the signal we get is extremely important. The example that Gord just mentioned of the Bushveld complex in South Africa is very well known to miners around the world. It's an enormous deposit containing all sorts of valuable metallic elements, things like platinum group metals. It contains some chrome in there, and it's all hosted in a very large folded complex of igneous rocks and metamorphic rocks. So being able to find similar features in the vicinity, Gord mentioned Malopo Farm, that's hugely advantageous for explorers, particularly if you can fly rapid surveying across the area. So that's great. We can spot things nowadays with the resolution, things like channels, placer deposits. So again, you can get things like gold in placer deposits. You can also get some precious gemstones. So I have here a couple of examples of things like sapphires. So I don't know if you can see that, but that's a rough Padporitia sapphire. You'll most often see that as a sort of orange-purple stone in an engagement ring. Or we have blue sapphires. And we also find economically important mineral deposits. You might hear the word coltan mentioned, which is a columbite tantalite mix. This is a fairly dense piece of coltan material as a crystal. These are the sorts of deposits that are changing the world. These are the deposits which are finding the resources, the critical resources for the next 10 to 50 years to help us undergo energy transitions and technology transitions. So bits of these things are in our phones, they're in our TV screens, they're in pretty much everything. We also have a really growing need for renewable energy and ways of utilizing sustainable energy. So the hunt is on at the moment for lithium. You'll have heard that probably in the news. I don't actually have a piece of evaporite lithium, but I do have a piece of lepidolite, which is one of the main lithium ores that you can get from features called pegmatites. I also have some spodumene here, which is, again, a nice example of a lithium mineral. So these are the things that people are chasing. And actually, with things like FTG to hand, we can start to spot the anomalies, which can be indicators of these kinds of deposits. As Gord mentioned, some of the things that you need to bear in mind as an explorer is that you need to know how big is your anomaly, and therefore how big might your target be. You need to know how deep the deposit might be. That's extremely important to us. And also, what is the shape of the anomaly? So I think FTG really takes us to the next level with that. A project that I've worked on was very much focused on fault geometries, where mineral deposits were hosted in very fine-scale faults. And fault deposits are quite nice because as a mineral collector, they have voids and holes where really nice, pretty minerals can grow as well. So here's a nice piece of cassiterite from South America. This is a beautiful piece of a tin ore. And this is the sort of thing that people will also be looking for using techniques like FTG in the future, where there are narrow bands of material. I just have to say that although that is extremely pretty, more often than not, in an industrial context, it comes in things like this from Cornwall in the UK, which was for a long time one of the biggest tin producers in the world, certainly during the 17th and 18th centuries. So although it's not very pretty, this was actually extremely valuable to the people of Cornwall and to the people of the UK and really the whole world. So we shouldn't overlook some of the importance and relevance of these minerals as we go forward. Gord mentioned it's important to be sustainable. So one thing I would finish with really is the idea that airborne surveying is one of the least disruptive forms of surveying we can possibly do. If you're flying in a plane, you can go above areas of high relief, you can go above urban areas, you can fly really wherever you need to go with causing minimal disturbance, and yet you can still see detail. And another final advantage of FTG and the airborne method is that you can actually infill data so that you can do some reconnaissance surveying to see what's going on in the area. And as soon as someone like myself or Gord spots something that's of interest, you can go in and shoot more detailed data whilst you've still got the plane in the air. So I think that's really, as an explorer, where I see the greatest value and in terms of resource applications. So I think that for me is probably the benefits. So thank you.
Thanks, Tim. I think you've sold FTG for me. But in addition, something important here, though, is that it's true. I want to emphasize, as you said, Tim, that both magnetic and gravity surveying are 100% passive technique. And as such, they have a very low environmental footprint. They're fast. They're relatively low cost compared to other techniques, certainly seismic, compared to drilling. They can cover very large area quickly. And I think that having low impact, low environmental footprint is very relevant and important in times where company and stakeholders, and including us contractor, have to carry out really responsible and efficient exploration program. We just can't go underground and shoot, bring vibro-sized truck everywhere and start drilling. We have to limit the impact of exploration as much as we can. Of course, limit costs too, and be more efficient in our targeting. So, which is really why I think airborne geophysics is very much an ingredient for carrying this out successfully. And I think, Tim, you need to open a local museum with all your samples.
Don't tell anybody where I live.
That really was quite an object lesson. Very, very good stuff. Well, thank you both so much for joining us here on the podcast today, Tim Wright and Gud Poulican, for joining us here on A Propensity to Talk Density. It's been an absolute pleasure having you on, and thank you so much for sharing your insights.
Absolute pleasure too. Thank you very much.
Thanks, Tyler. Thank you very much. Thank you, Tim.
Absolutely. And everyone, thank you for tuning into this episode of A Propensity to Talk Density. We appreciate it very much. Of course, make sure to tune in for further episodes of the show, and make sure to go visit the website for Bell Geospace as well to stay up to date with everything that they're doing in this world, and subscribe to the podcast. Stay up to date with the latest episodes, and stay tuned. We'll be back soon with more episodes. But until then, I've been your host today, Tyler Kern. Thanks so much for listening.